Okay, so coming now to the second half of the lab. So in um, some of the previous videos, we talked about the signature ordered, where I guess that was Monday's videos. We talked about ordered, where we have a type T with a comparison function. And this kind of signature is meant to be used descriptively rather than prescriptively. That is, unlike counter, where we're intending it to be all we know about the type in question. For ordered, we don't intend this to be all we know about the type T is that we can compare it, because then, of course, we could never make any. We just want to describe that this particular type has a comparison function. So for ordered, the intention is that we want to leak the information that T is actually int, or T is actually string, or T is actually floating point, like we did in the videos on Wednesday. We don't want to kind of leave that unknown. So in this case, we just define T to be whatever we want it to be. We don't define it to be a hidden data type like we were doing above. Okay, and so what I want to do now is an example of kind of type-directed programming. So the first problem was just to order year, month, day pairs, right? So like we'll define the type T to be that, where like 1999, comma 5, comma 1 equals May 1, 1999, right? So like we're representing dates as first the year, then the month number, then the day. And so we want to order these lexicographically. So compare would get in year 1, month 1, day 1, year 2, month 2, day 2. Okay, and so if um, we compare y1, year 1, and year 2, and we get equal, then what we need to do is we need to continue checking things, and otherwise we want the comparison. So like if we're ordering things lexicographically, right, that means like first we want to compare the years. If the years are equal, then check the month and days, and otherwise, like if we've got, for example, May 1, 1999 is greater than January 1, 2000, 1998, because 1999 is bigger than 1998, right? So first we're checking the years. Otherwise, we want to do the same thing. So compare month 1 and month 2, and if they're equal, then finally compare day 1 and day 2, and otherwise whatever we get is what we get. Okay, and so now we can do things like year, month, day order dot compare of 1999 May 1 and 1998 of 1 1, and we see that we get greater. If we did 2000, here we get less. If we said 1999, then it would be greater because May is bigger than January. If they were both that, that would be that. If that was that, that would be that, and so on. Okay, so hopefully you get the idea there. Okay, so what we're doing here is we're ordering triples, right, int with int with int, by first comparing the first component, and then if that fails, comparing the second component. If that not fails, but if they're equal, compare the second components, and then if they're equal, there's compare the third components. And so we can actually get this code out of applying kind of a more abstract version of it twice. So if you give me two ordered types, right? So remember, an ordered type is any type that has a comparison function packaged with it. If you give me two ordered types, then really what we were doing there was a couple of times giving an order on pairs of elements of those two types. So if you give me x1 and x2 and y1 and y2, where x1 is of type t dot o1 dot t, sorry, that's supposed to be y1. Y1 is of type t dot o2 dot t, x2 is of type t dot o1 dot t, y2 is of type t dot o2 dot t, and if they're equal, then I can compare y1 and y2 according to the way that I compare y1 and y2, and otherwise I'll return the answer. Compound type constructor. Sorry, t dot o1 dot t, t dot o2 dot t. Okay, so the idea is that two orders is a signature. What's inside two orders? Well, it's two ordered types. I'm naming the first one of them O1, and I'm naming the second one of them O2. And so then when I have two ordered types, I can say that, well, take the type from the first one and the type from the second one and make the type consisting of pairs of elements there. So down here, for example, I could say structure int string order is pair order, where I give it as input the structure O1 is ints ordered by less than, and then let me make another one up here for, we did this in Monday's video, strings ordered by less than string dot compare, right? So I can instantiate the functor where O1 is ints and O2 is strings ordered by less than. And then I can say is order dot compare of the pair 1a with 2b and get less, and 1a with 1b and get less, and 1a with 1a and get greater, because when you compare strings, uppercase letters are considered to be less than lowercase letters by ASCII code, and so on, right? So like I can feed in any two types that have a comparison function and build up a comparison function on the pairs. And so I could similarly do that for ints and ints rather than ints and strings, and call it, I don't know, I order, and then for I order, when I compare them, I would do, you know, a pair of ints, and ints is an example there. And so the thing that we're able to do here then is, this is another example of why you want SML to propagate the type information, because when you do this, we're saying, oh, I'm going to take O1 to be ints and O2 to be ints. And so then when I do the pair order, T is O1's type plus times O2's type, which is int char int. And so I can apply this to pairs of ints because it leaks the information that ordered is the output type of the order is exactly the type that you construct it to be. So the whole point is that we want this to be not hidden when we're using functors in this way to build up code on bigger types from code on smaller types. Okay, and this style of programming is sometimes called a type class. That is, you have a signature like order that describes a property of a type or a structure on a type. It has a comparison function. And then you think of building up that structure on a type compositionally by piecing together the structures on smaller types. And so now we can finish off the example because the structure year, month, day order is just the pair order on the structure where O1 is ints and O2 is ints ordered. Okay, and so then I can do my year, month, day order dot compare of, what was the example? May 1, 1999, May 1, and 1999, January 1, and I can do my comparison there. Okay, so what we're doing is we're building up the ordering on what we wrote out by hand as int star, int by chaining together I have an ordering on ints, I have an ordering on pairs of ints, I feed those into pair order, and I get an ordering on pairs of ints and pairs of ints. Okay, and so that lets you build up comparison functions for bigger types, ordering them lexicographically. So lexicographically is dictionary order, right? Like first you compare by the first letter of the word, and then you compare by the second letters of the word if the first letters of the words are equal. That's what this pair order functor is implementing. It's implementing lexicographic ordering on pairs. And so then chaining that together, you can lexicographically order like big tuples of types by just applying the functor a bunch of times. So in the code we wrote by hand, you can sort of see that there's the, if the comparisons are equal, then compare some other stuff, otherwise the same, right? There's sort of the repetition of that process twice. And the way that we've abstracted that is we've written that if the first things are equal, then compare the second things, otherwise whatever you get is what you get. And then we don't have to repeat that code twice here. Instead, what we do is we just use the pattern. That is, we use pair order once to order ints and ints, and then we use pair order a second time with that first one to order int and int pairs. Okay, so that's the solution to the functor part there. Okay, so what's coming next is a homework on modules where you're going to get to sort of play with some of these concepts and implement some basic dictionary stuff, and that'll involve just a little bit of module stuff in the sense that you'll be implementing some new stuff inside of a module and implementing a client module that uses it. And then in the final homework, you're going to be using that dictionary implementation that you extend in this week's homework in order to do some machine learning via naive Bayes text classification. Okay, so that's what's up next. Talk to you later.